Okay, this is the first of a couple of lectures here for chapter 26, which covers simple circuits. Let's go through the basics. Okay, first of all, take a look, or make sure that you take a look at my short demonstration video called EMF and Terminal Voltage. Let me begin by giving you an explanation of what it was that you saw. Okay, so let me go ahead and just draw a battery. Like so. We'll say that right here is the positive side, here is the negative side. Okay, a battery more or less consists of two things. Okay, first of all, there's the initial potential difference that I previously have described to you in the context, for example, of my simple demonstration involving a chemical battery, which I demonstrated for you right at the beginning of chapter 24. So that's the original potential difference. Here and here. Okay, this is what you saw in the demonstration when the current was not flowing. This is referred to as the electromotive force, also sometimes abbreviated as EMF. The word force here, however, is a misnomer. All that you're seeing is the original potential difference. In a 9-volt battery, this is basically the 9 volts that you're buying, for example, when you see it packaged. The symbol that we use for this potential difference, the electromotive force, the EMF, is the following, like so. Okay, it's measured, of course, in terms of volts. Okay, and then the current was flowing when I flipped the switch such that the light bulb lit. Okay, when that happens, within the battery itself, there's an energy transfer. Chemical potential energy, for example, is being converted into the kinetic energy of the electrical current. Okay, that energy transfer process, however, is not 100% efficient. Some of that energy is going to be converted into heat during the chemical reaction itself. In other words, within the battery behaves as if there's a resistor that is present. This is referred to as the internal resistance. There's actually no resistor there that is present. Instead, what's really happening is that you're just losing some of the energy as heat during the conversion process. But this behaves as if there is a resistor within the battery. Once again, we refer to this as internal resistance. We use the symbol small r for that, and we measure it in terms of ohms. Like so. So here's the internal resistance R. Therefore, when the current was flowing, and I then placed the leads across the battery, what you were measuring was this total potential difference while current is flowing. Picture the current as flowing like so in this direction. Okay, that voltage that I measured, which was less than the EMF, that is referred to as the terminal voltage. The terminal voltage, for example, is less than 9 volts. Okay, how do we actually calculate the terminal voltage? Well, we do so by basically following the current through the battery. What I'm going to do is I'm going to add up the potential differences from one side of the battery to the other. I'm going to start here at the bottom of the diagram and then go up to the top. As I do, this right here is low potential, this is high potential, and then as the current flows through the battery, and this is how we think of it, as the current flows through the battery, the conventional current falls from high to low potential. So across the internal resistance of the battery, this right here is high potential, this right here is low potential. And now let's just add up the potential differences as I go from the bottom of the battery to the top. Okay, so as I do, the first thing I do is I go across, as we say, the EMF. I start right here at low potential, and I end up right here at high potential. Therefore, the potential difference, this amount of volts, is a positive number. Final minus initial, we go from low to high potential. Therefore, the final value of the potential is greater than the initial value. Therefore, the potential difference is a positive number. Once again, this is what I was measuring when the current was not flowing. However, when the current is flowing, now we're going to follow the conventional current across this resistor. As we do, the conventional current falls from high to low potential. So then therefore the potential difference, which just obeys Ohm's law, it's I times R, it's a negative number because the final value is less than the initial value. So this quantity right here is what's referred to as the terminal voltage, which I'll just now write as V. Notice that the terminal voltage here, V, is less than the EMF. So the EMF is the 9 volts that you would buy on the package, for example, for a 9-volt battery. But while the current is flowing and the resistance here is present, therefore the terminal voltage is less than the EMF. That's what you saw in the demonstration. Okay, let me go ahead and pause here. That's just part 1.